last of the spectroscopy talks. All right, we're going to talk about UV vis or UV spectroscopy, and it gives you actually information on the electronic transitions and allows you to determine bonding patterns, particularly for conjugated pi bond systems. Okay, we have uses for it, quantitative analysis. We can look for concentrations using Beer's law, so we'll go through that. Okay, we can compare it. So basically, if you have a known substance and you know what the UV vis spectrum looks like, then you can take your unknown, run it, and then compare the two to see if they're exactly the same. You know that you have that compound. And we can use it to estimate the amount of conjugation in a system. All right, so what transitions are we looking at? N bonding means non-bonding. You're looking for N to pi star or pi to pi star excitations, these two. Okay, and that occurs in the UV range, vis range, so 200 to 400 and 400 to 800 nanometers, closer to this range. Okay, so let's just go through. The greater the conjugation, the lower your frequency, the longer your wavelength. So in ethylene, here's my HOMO, here's my LUMO. You do your pi to pi star. That's what we're looking at for the transition. If I do a pi to pi star here, it's at 171 nanometers. It doesn't really register too well on the UV vis spectrophotometers that we use. However, here with 1,3-butadiene, with just a simple conjugation, I'm looking for my HOMO to LUMO excitation, and that occurs at 217 nanometers, and that we can definitely see on a UV vis spectrophotometer. How does it work? Looks very much like what our monochromator for the IR looks like. You have a light source, goes through the diffraction grating. We have basically this going through a rotating disc. Your beam gets split. One goes through your sample, one goes to a reference cell, okay, and then basically they get recombined, subtract off your reference cell, goes to your detector, and then you get your chart recorder, and that tells you what the spectrum looks like. If you know Beer's law, the absorbance that you detect, okay, is going to be equal to epsilon CL, where epsilon is your extinction coefficient. Remember, that value is dependent on the wavelength of detection. The same compound, but if you're looking at 400 nanometer wavelength versus 600 nanometer wavelength, you will have a different molar extinction coefficient. C is the concentration of sample in molarity, and length L is the length of your cell. Usually it's 1.00 centimeters. Okay, when you do carry out UV vis spectroscopy, make sure you choose solvents that do not absorb at the same frequencies as your samples of interest, because if you do, you're going to get absorption not due to your sample, but due to your solvent, and that's what you want to avoid. Okay, so here's citral. You guys have made citral. Basically, if you look at neural and geranyl, they have very similar, okay, absorbances, but there's a slight difference. So you can actually do a comparison between the two. Okay, now remember the difference between this is just a cis and trans across a double bond. Okay, if you look at the conjugated pi system, some representative molecules, of course, ethylene we already discussed was 171, single isolated double bond 182. These guys are not conjugated 180, so they're very much, the wavelengths are shorter, a little harder to detect. But once you get into conjugation, look at this, it increases my wavelength, okay, fairly significantly. We can now start detecting it. And as I get longer and longer conjugations, you can see that my wavelength increases. How much does it increase? So if you see what the wavelength is for your system, you can get an idea about your conjugation. Likewise, if you know the molecule, you can kind of estimate what the conjugation should be. So when we talk about Diels-Alder and the S-trans, the S stands for is across a single bond, just to make sure for your diene that it's in the trans orientation. The base value is 217 nanometers. If it's conjugated to another double bond, then it increases basically your wavelength by 30 nanometers. If you have an alkyl group on that first diene, you're going to increase it 5 nanometers. Alkoxy groups or acetates don't affect it. If you're in a ring and one of the double bonds in your diene system is exocyclic, you're going to increase your wavelength by 5 nanometers. So for example, here is my diene. I've drawn it in the trans orientation, right? Or it's been drawn in the trans orientation. I have 1, 2, 3 alkyl groups. And for every alkyl group, you increase it by 5 nanometers. So 15, we expect it to be around 232. That's what we observe. Here, again, is my base. All right. Okay, that again is in the trans orientation. This one is exocyclic, that are outside of a ring. We're going to add 5 nanometers. Alkyl group attached here, alkyl group attached there. Add 10, 232. We observe 230. Here, also, this is an S-trans diene. So we're going to say 217 is my base. This alkenyl double bond group is exocyclic. Here's my ring, so it's exocyclic. Therefore, I'm going to add 5 to that. That double bond here has 1, 2 R groups to it. That means that I'm going to add 10. 232, we observe 236. Okay. What about this one? Okay, that's my double bond. So if we just kind of ignore here, you can kind of see why they say this is exocyclic. So you're going to add 5. I have an R group here, I have an R group there, and I have an R group there. 3 times 5, 15. So you add this 237, what you observe is 235. Let's take a look at this group. That's my S-trans. Here's my ring. This is exocyclic. So I'm going to add 5. Okay. Oh, and look at this. What do I add if I have another conjugated carbon double bond carbon? 30. And now look at this has 1 alkyl group, 1 alkyl group, 1 alkyl group, 3 alkyl groups, 15. We predict 303. We observe 304. Here, don't have to worry about the exocyclic. I have my trans here, 217, and I add the 30. I don't have any additional R groups. 247, but it's observed at 258. All right? So that's how you use the Woodward-Fieser rules to help you to predict what your wavelength max should be for your compound. We've talked about carbon-carbon double bonds, but we should talk about carbon-oxygen double bonds. And we are also, again, looking for pi to pi star. The base for that, if R is an alkyl group, so you have a ketone, the base is 210 nanometers. If it's an aldehyde, it's slightly higher at 215 nanometers. You can have an alkyl group at the A position, or you can have them at the B position. This one, you add 10 nanometers to your wavelength. This one, you add 12 nanometers. Again, if this is exocyclic, 5. If I conjugate it further, 30 nanometers. Now, what about this N to pi star we were talking about earlier? Well, N to pi star weak absorbances, They're weak absorbances, so my extinction coefficient is low. However, it does occur at the range where the maximum is between 280 and 300 nanometers. Okay, so your dry lab for your UV problem set then is based on the Woodward-Fieser rules. You're going to determine what the maximum wavelength is for UV vis for these 4 structures. And you're going to have to determine which of these 3 has the longest wavelength. Okay, good luck and hope you're safe.